n plus 1 to the n over n to the n. Do y'all see these? This one here and this one here, right? That's all we're left with? You could put those both in a parentheses, couldn't you? You could do n plus 1 over n to the n power. Yeah, so you know in the last problem I said you could push this limit in here and ignore the power? You could do that because that power was 4. It was a constant. This is not a constant. So you cannot push the limit inside of this. So what's happening here? This is, well, hold on. Hold on a second. Wait a minute. Wait just a minute. Wait just a minute. Okay, so what do I do? Yeah, split this into 2 fractions, right? N over n and then 1 over n together, yes? I did that for a reason. I'm hoping somebody in this class recognizes this very important limit from Cal 1. No, it's okay if we don't. If we don't, we have to show what it is then. Yeah? Okay, we move on. We're going to show what it is. Let's see what's happening here. So as n goes to infinity, what does this go to? That goes to 0, right? And this goes to infinity. So what is the inside of this approaching? What is this inside getting closer and closer to? 1 plus 0, which is 1. And then it's being raised to the what? Infinity. And that is an indeterminate form from Cal 1. Because this number, is this number actually the number 1? No, it's getting close to 1, right? It's 1 plus this tiny little amount, right? So this is an indeterminate form. We can't tell what the answer to this is. We have to go figure this out. So let's go figure it out. This will be a good review of L'Hopital. So do any of my Cal 1 students, now I'm calling y'all out. Does anyone remember how we handle a limit when you have 1 to the infinity? How at least I did it in class? We're going to do some algebra. Yeah, what are we going to do though? Pardon? Drop to the bottom will be the step after the step we need to do first. So what you're talking about is dropping 1 down. We can do that when we have 0 times infinity. Right now, we have 1 to the infinity. You can't drop anything. Okay, so when you see this, right, there's actually 3 different forms that could look like this that are indeterminate. You have something to a power. What I teach my class is that, yep, we're going to bring a natural log. We're going to call this limit that we're going to try and solve for, let's just call it, I don't know, well, L, right? Isn't it L? Because this is we're doing ratio test. This limit is going to be L, and it's either going to be less than 1 or greater than 1 or equal to 1, right? So I'm going to call this L. We want to know what it is, right? So now what I'm going to do is I'm going to take the natural log on the left side, natural log of L. And then on the right side, when you do a natural log, you can pass the natural log through the limit. You put the natural log in front of all of this now, like this. And what does that allow you to do? Bring the n out. It allows you to drop the n in front of the natural log. That's the whole reason we have to bring the natural log in on both sides. And in order to implement the natural log on both sides, I had to have an equation. I had to have 2 sides, so that's why I called this L, simply so I could have 2 sides of an equation to work with. So now, pop this out. And when I pop that out, I now have this. Left side, natural log of L equals limit n goes to infinity. Okay, the n came out in front, and then I have natural log of 1 plus 1 over n. This is a famous limit, by the way, when we get this answer, you'll see. Now we can do what you're referring to. If we let n go to infinity now, where does that go? Infinity, okay. And then what about the other part? What does the other part go to? Oh, infinity times, that goes to what, 1? But what's natural log of 1? 0. So you get infinity times 0 is what it's headed towards, right? That's still an indeterminate form. So now you drop 1 down. So I'm going to take this n and drop it to the bottom. Notice I'm keeping my equation the whole time I'm doing this. So I'm going to take this n, I'm going to drop the n to the bottom. When I drop the n to the bottom, what does it become on the bottom? N to the negative 1, or I'm just going to put 1 over n. Is that okay? I'm just going to bring this n to the bottom as a 1 over n on the bottom. Isn't that the same as having an n right there? Right? Okay, but the whole reason we do that is because now what happens when you do n to infinity? What does that whole top go to? 0. What does the bottom go to? 0. And now that you have 0 over 0, you can use L'Hopital. This is the standard approach. When you have something, does anyone remember what the indeterminate forms are where you do this method? 1 to the infinity. There's another one. Infinity to the 0. No, infinity to infinity would be okay, because that's just big and getting bigger, right? 0 to the 0. Good. 0 to the 0. Those are the only 3 that you have problems with. What I heard some others. What were the others I heard? I thought I heard, well, infinity to the infinity. That's not indeterminate because the base gets big, exponent gets big, that just gets big, right? That goes to infinity. 0 to infinity. So this is one that a lot of people are like, okay, this seems awkward, right? But think about what's happening. The number here wants to get small, right? Wants to get real small. What happens when you take a small number and raise it to a power? It gets smaller, right? So it's like this one's like, I'm trying to be small, and the exponent's like, well, let me help you, right? So this actually goes to 0. Any others you can think of? Okay, so that's not a power. This is infinity minus infinity. That's indeterminate as well. And that's a different method. We use a different method for this. We do like factoring or common denominator or something like that. So this is indeterminate, but it doesn't fall into this pattern. What I'm looking at is things that have exponents that would require us to pull something out, which means natural log. Okay, I need to get back to this. All right, so over here, now we can do L'Hopital. Natural log L equals, by L'Hopital's rule, limit n goes to infinity. Okay, here we go. Derivative of the top. Well, what's the derivative of natural log of anything? 1 over that anything, right? 1 over whatever was in here, times, now you have to take derivative of what was inside. What's derivative of 1? 0 plus, what's derivative of 1 over n? The derivative, not antiderivative. 1 over n, take its derivative. It's the same as n to the negative 1, take its derivative, which is negative n to the negative 2, which is negative 1 over n squared. All right, that's a derivative of 1 over n. So I'm going to put here times negative 1 over n squared. Right, that's a derivative of what's in here. But then over, now the derivative of the bottom. Hey, look, 1 over n, what's its derivative? Negative 1 over n squared. Didn't we just get that? And guess what? They go away. And now take the limit of that. 1 over infinity goes to 0. 1 plus 0, 1. 1 over 1, 1. This is 1, isn't it? Right? So we get natural log of L equals 1. Okay, what are we trying to find, though? L, right? Not natural log of L. We need L. So how do you get L from that? Exponential. You have to kill off the log, so you bring in its inverse, exponential. So we take basically exponential on both sides. So you do e to the natural log L equals e to the what? 1. So this side is L. L equals what? E. E is a number, isn't it? What is E about? 2.718? It's what? Bigger than 1, which means this series diverges. Therefore, this diverges. Now, you might be saying, hey, shit, you're not convincing me that the ratio test is better. Okay, but I'm telling you, you try a different test on that, it's not happening. All right, you're going to have a lot of trouble. So try and remember that limit. It comes up quite a bit. That's E. That's another way you can represent the number E. You know, like pi, we know what pi is, right? What's the definition of pi? What's the most simple definition of what pi is? Circumference over diameter. Done. Well, you're telling me what it is, right? 3.1415. But if you were to try and explain to somebody, right, what is pi? Take a circle. Draw its diameter. Measure the circumference. If you take that circumference, divide by that diameter, you get what pi is. That's a very simple way to explain what pi is, right? What's E? Oh, well, you can define E to be this. The limit as n goes to infinity of 1 plus 1 over n to the n. That is one way you can define what E is, right? One of many ways you could define it. Okay, let's go to our next example. Are y'all doing all right? All right, this next example is strange as shit, like strange, all right? So pay attention, because this is an awkward notation, okay? It's an awkward notation that we have not seen. I've never presented anything like this to you before. Right? Oh, the sum's not here, sorry. Okay, so we want to know if this converges or diverges. We have 2/5 plus 2 times 6 over 5 times 8 plus 2 times 6 times 10 over 5 times 8 times 11. There's a pattern here. Let's see. 2 times 6 times 10. Each time I go up, these numbers are increasing by what? 4, so it should be 14 over the bottom 5 times 8 times 11 times, and these are going up by 3 each time, right? So I should have what, 14 again? Don't cancel those 14s. Let's just try and get the pattern going, okay? What would the next one be? 2 times 6 times 10 times 14 times 18 over 5 times 8 times 11 times 14 times 17 plus ... Holy crap, right? You look at that, it's confusing looking. Well, let's try and see if we can write this as a series, like a sum. Sum, n equals 1 to infinity. All right. Let me put on the board what is not going to work, all right? What people will look at this initially and try. We said these are going up by 4 each time, right? On the top, these are going up by 4 each time. And starting with what? 2. So can you create something that goes up by 4 each time but starts at 2?
2n plus 4.
2n plus 4. We're starting at n equals 1. If you tried 2n plus 4, if you plug in 1, we start at 6, right? Right?
Yeah.
Okay. Someone else? Start me at 2 and increase by 4 each time. 4 to the n plus 1. 4 times n. Okay, we'll just start right here. Right here, what would we start at?
4.
We get 4, then we would get 8. So what do we need? We need to tweak this. This jumps by 4 each time, but doesn't start at 2. Starts at 4. Minus 2. There. Try that. Let n be 1. What happens if n is 1? What do you get? 2. Right? If n is 1, you get 4 minus 2 is 2. Let n be 2. You get 4 times 2 is 8. Minus 2 is 6. Right? Do y'all remember this? We did do this. If we want something to jump by 4, we put 4n, and then we just subtract or add a number to get where we want to start it. So students will make a mistake right now of putting 4n minus 2 here, and then see if you can do the same thing on the bottom. We need to jump by how much on each one? 3 starting at 5. So how do you do that? Jump by 3, so I need 3n. And then I need to start at 5. When I plug in 1, I need this to be a 5, so what? Plus 2. If I plug in 1, I get 3, plus 2 is 5. Plug in 2, I get 6, plus 2 is 8. Got it? This is not correct, though. I mean, if you do this, write it out. What would you get? Let n be 1. What do you get? You get 2/5. Okay, great. It got me the first one, didn't it? Plus, now what would the next one be? 6/8. And then the next one? 10 over 11. Is that what we have? That's not what we have, right? That's not what we have. So this does not work for what we're given. So we have to use a slightly different notation, which is like I said, I'm showing this to you because we haven't seen this before. This won't work though. Here's what I need to put in here. It's going to look weird, but just bear with me here. This top is going to be 2 times 6 times ... until I get to 4n minus 2. Now, 4n minus 2, isn't that the formula I just used a second ago? But what I'm telling you is that you're going to do 2 times 6 times blah, 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 and stop when you get to this one. So I'm showing you a pattern of the multiplications up here, right? You see the pattern? And on the bottom, I want you to do 5 times 8 times ... and I want you to stop when you get to 3n plus 2. That's the notation. Now let's check to see that this works. If n is 1, where do I stop? At 2 right here, right? So I'm going to start at 2 and stop at 2. So I'm going to have a 2 here. And then if n is 1, where do I stop here? 5. So I'm going to have 5, and that's all. Plus, now let n be 2. If n is 2, where do I stop? 4 times 2 is 8. Take away 2 is 6. So I'm going to go 2 times 6, and I'm stopping at 6. So it's giving you a place to stop doing that pattern. If n is 2 here, we got what? 6 plus 2, 8. So I do 5 times 8 and stop at 8. Does that make sense? It's a weird notation, right? It seems like in math we should have a better notation for something like this, right? Doesn't it seem like we should have a better notation? We actually do, but we're not even going to cover it in this class. Everyone here is familiar with this, right? If I write that, I write this, right? If I were to write let me just do this, 4n minus 2, right? If I do that, if I just said do that, then this would mean what? 2 plus 6 plus 10 plus 14 plus forever, right? That's what that would mean. But what if instead of that, I wanted you to not add, I wanted you to multiply them, right? Well, we have the capital Greek letter S, right? Sigma, which stands for sum, right? What if I want to do a product instead? We have a different notation. We don't use the Greek sigma. We use the capital Greek letter for pi. That's a capital pi. And we put n equals 1 to infinity. And now, what does this mean? Of the formula, sorry, 4n minus 2. Okay, so what does this mean? Let n be 1, you get 2. But instead of adding, because it's a product, times, then 6, then times 10, then times 14, times ... I'm just showing you there's a whole other notation we don't study in this class. It's a product instead of a sum. It would be perfect for this, but the book doesn't go into it. I'm not going to go into it, so we're going to be stuck with this crappy notation, all right? All right, let's try one more just to verify it works. Now, this was n is 1, n is 2. Now, when n is 3, where do I stop? 4 times 3, 12 minus 2, 10. So I'm going to go 2, 6, 10, and stop at 10. On the bottom, we get the 5 times 8 times 11, plus dot, dot, dot. OK. Y'all all right with that?
So for the way you write it, do you need to have just the first numbers? Do you need to have the first two numbers times dot, dot, dot?
You don't have to have the first two. You could have at least the first one, but you have to have like dot, 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 and then this, right? If we take all that away, then we already said that's wrong, right? It doesn't give us what we want. So you have to show that there's a pattern of multiplication up here.
So you need at least the first number.
At least the first one. First one here, dot, dot, dot would have been fine. I just put the first two. All right. Does it converge or diverge? Ratio test, right? Ratio test. Now, yeah, let's just go to it. Ratio test. All right, so I want to take the limit as n goes to infinity of the absolute value. All right, let's do the easy part first. Let's do the denominator. The denominator is just that formula, isn't it? Without any adjustments to it. So it's weird, but it's 2 times 6 times dot, dot, dot. And then here we got 4n minus 2. And then on the bottom, we got 5 times 8 times dot, 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 and then 3n plus 2. OK, that's the bottom, right? That's just a sub n. Now what I need to do is I need to plug n plus 1 into this, right? Right there and right there. Right there and right there. Let me do it. It's 2 times 6 times dot, 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 times, leave a space. I'm going to leave a space. Just trust me on this one. There's two ways to get the last one. There's two ways to think about it. One way is to take this and replace the n with n plus 1. Right? Just replace the n with n plus 1. What would you get? 4n plus 4 minus 2. So that would be 4n plus 2. Right? That's one way to do it. The other way to do it is just think about what happens as you go up in these numbers. What happens each time you go up? You add 4, add 4, add 4, add 4. So wouldn't the one after this just be that plus 4? What's this plus 4? That, right? So I'm going to put that right here, 4n plus 4. Or sorry, not 4n plus 4, 4n plus 2. And then over, then on the other one, 5 times 8 times dot, 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 leave a space, and then see if you can follow that same pattern here. What's happening on this bottom one? Each time you go up, you're what? Adding 3, right? So if I take that, and the next one down would be what? 3n plus 5, which is what you would get if you just replace that with n plus 1. So 3n plus 5. Now, I left a gap intentionally. The reason I left the gap is because I'm going to hope that some of this stuff cancels out, right? Like if I have any hope of figuring out what this big ugly thing is, things are going to have to cancel, won't they? OK, so I left the gap because I want you to remember what is sitting right in front of each of these. What's the one right in front of this one? 4n minus 2, right? And what's the one right in front of this one? 3n plus 2, isn't it? It was the one right before it, right? And the reason I want that is because they're right here, aren't they? They're right there. OK, so let's clean this up. I'm going to write it over here. So this is equal to limit n goes to infinity All right. Let's write the top. 2 times 6 times dot, dot, dot times 4n minus 2. And then the one next to it was 4n plus 2. And then over the 5 times 8 times dot, dot, dot. And then it was the 3n plus 2. And then the 3n plus 5. And now I'm going to take the bottom fraction. I'm going to flip it, right? Reciprocal. So multiplication now. And I'll have the 5 times 8 times dot, dot, dot to the 3n plus 2. And then the denominator of this will be 2 times 6 times dot, 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 and stop at 4n minus 2. Questions on that line? Do y'all see what happens? Lots of good stuff, right? Lots of good stuff. This 2 cancels with this 2. This 6 cancels with this 6. All this dot, dot, dot stuff in here cancels with all this dot, dot stuff, all the way until I get to where? 4n minus 2 to 4n minus 2. But the 4n plus 2 doesn't go anywhere, does it? No, it doesn't. Okay. How about the 5 and the 5, right? 5 and the 5. The 8 and the 8. The dot, dot, dot and the dot, dot, dot cancel. The 3n plus 2 and the 3n plus 2, right? A lot of stuff went away, didn't it? The only thing that stayed was this and this, right? Those are the only things that remained. And so now I can say limit n goes to infinity, absolute value 4n plus 2 over 3n plus 5. When you take that limit, you get infinity over infinity. So you do L'Hopital's rule one time, and you get 4/3, which is bigger than 1, which means this series diverges. Okay. Now, we good? If I would have given you this problem and flipped all these fractions over, I made this 5 over 2, 5 times 8 over 2 times 6, flipped them all, right? Just flipped everything over. Wouldn't it be all this work flipped over? And then our answer would have been what? 3/4, and that would have converged, right? It would have been less than 1, it would have converged. All right, so I believe if you look at the 2 quizzes I gave you, I handed them all out. Can you flip? Let me see here. Look at, there's one like this. Hold on. Is it number 6? Okay. Number 6? Yeah. Yep. Number 6 involves notation like this. So I just want you to see, like, it's not exactly like this problem, but it is similar in the sense that you have to understand what all that dot, dot, dot means in there. All right, I'm going to continue. Any questions? All right, we are done with ratio test, but we're going to have a lot more practice with it in the next section. All right, the next and last test, this is it. This is the final test, the root test. And the root test, we rarely ever use the root test. All right, the root test says that it's kind of this, it's almost exactly the same as the ratio test. But you know how with the ratio test, we do a limit of a ratio? With the root test, we do the limit of a root. So the root test says, if you've got some series, right, you're given this, then what you can do is take the limit as n goes to infinity of the absolute, well, it doesn't matter where you have the absolute value, but we'll put it like this, the nth root of the absolute value a sub n, like that, to the nth power. No, sorry, just absolute value. Sorry, I don't know what I'm doing. So with the ratio test, we did a ratio, right? With the root test, you're doing a root. But it's not just any root, it's the nth root. And then you're going to take that limit and see what you get. And it's the same three things that we have with the ratio test. If this is less than 1, that means the original series converges. If it's greater than 1, it diverges. If it's equal to 1, it fails. That's all on your sheet, right? It's all there? Okay, I'm going to do one example of this because it's not used much, just so you can see when it would be used. There's something that usually tells you that you should do it. So look at this right here. Sum n equals 1 to infinity of 3n plus 1 over 4n plus 3, all to the n. All right, could we use the ratio test? Sure. Could we try other tests? Sure. The thing that's going to make me want to do the root test here is that I have the entire thing being raised to the nth power. And if I take the nth root of something to the nth power, then that power will go away, won't it? So that's what's leading me to try root test. So root test, I'm going to take the limit as n goes to infinity of the nth root of the absolute value of this, right? The absolute value of this. Now, when I take that absolute value, do I really need an absolute value? Y'all tell me. Everything's positive, right? Good. So everything in here is positive. That's positive. This is positive. Positive number to a positive power should be positive. So that's all positive. I don't really need an absolute value. So I'm going to put 3n plus 1 over 4n plus 3 to the nth power. And again, you see, the nth root and the nth power kill each other off. And then you're just left with limit, n goes to infinity, 3n plus 1 over 4n plus 3. And that, L'Hopital, one time, what do you get? 3/4. And this is less than 1. Therefore, what does this do? Therefore, this converges. By the root test. Let's do the next one too, because that went pretty fast, didn't it? And then we'll be done with this section. Sum n equals 1 to infinity, 1 plus 1 over n to the n squared. That looks familiar, doesn't it? If I take that away and take the sum away and take the limit of that, we get e, right? So it looks similar to, but don't tell me that that's e. That's not e. What the hell? How am I going to do this? Okay, I'm going to try the root test. I'm going to try the root.